Hello everyone, Brendan here. I'm giving you away with my little ammonia looking type dog. So yes, here we got ammonia with its lone pair of electrons. So if you remember, we were talking about polar and nonpolar molecules. So this activity, or this little video I should say, is just giving me a bit more information about chromatography and what's the basis for it, so it can help you sort of with all the other types of chromatography around. So as it says in the first part, chromatography relies on secondary bonding which is dependent on polarity. Okay, so polar molecules will bond strongly to other polar molecules but not to non-polar molecules. So that first part, polar molecules will bond strongly to other polar molecules. So if we've got a stationary phase that's polar and we've got a polar molecule, then that polar molecule is going to stay fairly strongly to that stationary phase. So that's why it's very important, this statement here, towards chromatography. Okay, and vice versa, non-polar molecules will bond strongly to other non-polar molecules. Okay, but not to polar molecules. So once again, it's basically the same thing in reverse. So if the stationary phase is more polar than the mobile phase, okay, the stationary phase, which in our case was the paper, is more polar than the mobile phase, polar components will bond more strongly to the stationary phase and move at a slower rate than the non-polar components. So that's how we separate from our mixture our different polar and non-polar components. If the stationary phase is more non-polar than the mobile phase, non-polar components will bond more strongly to the stationary phase and move at a slower rate than more polar components. So you can have with stationary phases and mobile phases, they can be they can be a polar or a non-polar, depending on what you want to find. Okay, so for a given mobile phase, stationary phase combinations, the movement of any component relative to the solvent front, so that in the case with the water, or we looked at some hexane or isopropanol, is a producible property that can be expressed as a retardation factor, RF, for that particular component, which is what I want you to look at today. Okay, so, and the equation down here, so it's basically this distance moved by the component, so that's your actual component. So if I just go down to a slide, or if we look at this example here, so here we've got where they started, so how far along this component has gone in the stationary phase, how far it's moved along. So you've got that point there. Okay, divided by the distance moved by the solvent. Okay, so we can see that in this case, so the solvent line, wherever your water or your solvent ended up. Okay, so from there back to that baseline, so that's the length of your solvent from the starting dot to wherever it ended. Okay. Alright, so just if you need a bit of a recap, so polar molecules we've talked about. So if I went to example to water, water is a polar molecule. As you can see, it's got two lone pair electrons that represent lone pairs. Okay, oh, that's the other one there, you can see. So here, if I get rid of those lone pairs, you can see we've got our H2O molecule. Add in the lone pairs and they come up looking like that. So this end's going to be a negative end, and this end where the hydrogen atoms are is going to be our slightly positive charge. Okay, and we can look at some other molecules. So another one example, carbon dioxide. Okay, so this is a covalent bond, but it's a non-polar covalent bond. So here it's got a negative charge at both ends, a slightly more positive If I go to this one here, so here we've got carbon dioxide. So as you can see, if you look at the electron density as it gets darker, the electrons are more likely to be, and it looks like on those corners, doesn't it? Okay, so it's going to be more of a negative on both ends, but it's not a polar. There's no positive part to that atom. Okay, so that's a non-polar type compound. Okay, so what I would like you to do, hopefully you got some results between the four groups that you can actually measure some RF values from yesterday's prac. So if you could have a look at those, finish looking through those. Another thing I wanted to talk about also was the idea of adsorption. So you would have heard the term absorbing something, or and the other one is adsorption. So adsorption. Now the principle of that. Okay, I found the slide. So adsorption is when the molecules are actually just bonding with the surface. Okay, so that's the surface of your stationary phase. So the surface of a piece of paper is just bonding to the top, whereas absorption, which you would know, it actually gets absorbed into the liquid. And an example is water in a sponge. So the water is absorbed into the sponge. Whereas with adsorption, which is the important part of chromatography, is it's only bonded to the surface of that stationary phase. And then basically we've got the mobile phase, which will come over the top, and anything that's wanting to bond with that mobile phase more will move along, and the ones that not so will tend to stick to that stationary phase more closely. Okay, so a question you might get in a test type question is, it could be an example. Say in this example we used, and they tell you that a non-polar solvent was used, okay, for the mobile phase, and your question might be you might be given some RF values, okay, and you need to discuss which molecule in those is the most polar molecule. Okay, so if you've got a non-polar mobile phase, the non-polar molecules, the more non-polar molecules are going to move along faster, okay, and the polar molecules are going to be a lot slower. So in this case, the one on the very right would be the more polar molecule out of all of those. So that's an example of a test type question, and there's other ones just working out the RF values. Okay, so that's the basis for chromatography, and across all the chromatography methods that you will see in this section. We'll go into ion chromatography a bit more later, but if you can understand that process, that will help you understand how the other HPLC, gas chromatography, and any of the other TLC, etc., how they work. They all work on the same principle as that one there. Okay, so if you work through some more problems, and if you've got any questions, see me next week. Bye.